Now, let's take a look at the wind and figure out which runway you ought to use. The fat part of the windsock points into the wind. And so the wind here is basically coming from the northwest. The wind is coming down from the northwest and pretty much directly between the east-west runway and the north-south runway. So you could pretty well land on runway 26 and you would have a right quartering headwind when you did it. And if you landed on runway 26, what kind of traffic would you make? You'd make right-hand traffic because you've got a right turn from base to final. Also, in accordance with the wind, you could land north on runway 35. When you land to the north on runway 35, you would have a quartering headwind out of the left. That's where the wind is from. And what kind of traffic would you make for runway 35? You'd make left-hand traffic because you've got a left turn going from base to final. So as based on the wind, you could make left-hand traffic on runway 35 or right-hand traffic on runway 26, and in either case you would be landing into the wind. If you land on runway 26, if you choose to land on that runway, will you have a headwind or tailwind? You'll have a headwind, and will it be from the left? It will be from the right, a right quartering headwind if you land on runway 26. Take a look now at figure 45. Take a look at figure 45 and let's talk about some markings on the ends of the runways. Take a look first of all in the upper left corner at area A. And when you zoom in on the upper left-hand corner at area A, you'll notice that there are arrows on that runway before you get to the runway numbers. The arrows on that runway in area A mean that we have a displaced threshold. There is probably either an obstruction or a noise-sensitive area on the approach end of that runway that they want you to avoid. You cannot use that area where the arrows are for landings. You may not land there. But a takeoff wouldn't be any problem as far as obstructions or a noise-sensitive area there. So you can use that area with the arrows for takeoff, and you can use it for taxi. What you cannot use it for is not landing. You must land beyond the line that is labeled B, that is labeled Bravo. Now take a look below there at area Charlie. When you take a look at area Charlie, what you see is a row of X's across the runway, and that means it isn't a runway anymore. It is a closed runway, and you cannot use it. You cannot use it for takeoff or landing. Probably what happened here, you notice how close it is to the terminal and ramp area. They probably built that new terminal and then decided that this runway was too close, and so they X'd it off and they closed it. It's a closed runway. Now take a look over to the right at area E. When you take a look over to the right at area E, you see a bunch of chevrons on the end of that runway, and the chevrons means it is an emergency overrun. And there's only one thing that you can legally do on those chevrons, and that is to crash. The only thing you can do there is crash. You cannot land, you cannot take off, and you cannot even taxi there. It is simply an emergency overrun. The effective beginning of the runway for takeoff, landing, and taxiing is the line at line D. So let's take a look at this. Let's recap that. In area A, where you've got the arrows on the end of the runway, what can you not do in area A? You cannot land on those arrows in area A. Can you taxi there? Yes, you can. Can you take off there? Yes, you can, but you cannot land there. In area C, where we've got the X'd off runways, what can you do on area C? It's a closed runway. You cannot use it for takeoff and landing. Closed runway. But take a look at over area Echo. On area Echo, where we've got the chevrons down there, what's the only thing you can legally do in area E? Crash. It's an emergency overrun, and the only thing you can do on the chevrons is to crash. Now, take a look at figure 46. Take a look at figure 46, and let's assume the FAA gives you this set of runways and this traffic pattern indicator on the test and says, what runway should you land on, and what kind of wind can you expect? Well, take a look in the center of the segmented circle at this wind indicator. This is a tetrahedron, and think of a tetrahedron as if it were a delta wing aircraft landing into the wind. So if this aircraft is landing into the wind, and that's how a tetrahedron works, that means the wind is coming up from the southwest. You've got a wind out of the southwest, and it looks like if you landed on runway 22 going to the southwest, that would put you right into the wind, and indeed it would. However, taking a look at those runways, why is it that you can never ever land on runway 4 or 22 here? because they are X'd off. They are a closed runway, and you cannot land on a closed runway, so you cannot land on runway 22, even though it's the one pointed right directly into the wind. And you look at that and you say, well, heck, that's a real confusing thing. Why do they leave the traffic pattern indication then for if the runway is closed? Well, maybe the runway is only closed temporarily. Maybe they got a ditch across the runway while they're putting some runway lights in or something, but it's going to be back in shape pretty soon, and so all they do on a temporary basis is they put X's across the runway to close it. Okay, we cannot use runway 22, so what runway are we going to use instead? Well, if the wind is out of the southwest, are you going to want to land going north or going south? Which one? You're going to want to land going south. And if you land going south, which runway are you going to use? You're going to use runway 18 because you're going to be headed basically 180 degrees on that landing, touching down, hitting 180 degrees. Okay, you're landing to the south on runway 18. The wind is from the southwest, so what kind of wind are you going to have? You are going to have a crosswind from the right, a quartering headwind from the right as you land on runway 18. And the traffic you're going to make will be a right turn from base to final, so you'd make right traffic for runway 18, and you'll have a quartering wind from the right when you do it. See? Nothing to it. Let's talk now about taxiing an aircraft in a strong wind. If you have wind, what you want to do is expose the top of the control surfaces to that wind. And by putting the top of the control surfaces exposed to the wind, that will kind of push the aircraft down onto the taxiway and help keep it under control. Let's assume that you've got a quartering headwind. From wind from area Bravo here, if you've got a quartering headwind, what you want to do is have the aileron up on that side of the aircraft. In this particular case, on the right side of the aircraft, so that the top of the aileron will be exposed to the wind, and it'll push it down as opposed to getting under that wing and kind of flipping the airplane over. Now, what do you want to do with the elevator? If it is a nose wheel airplane, a tricycle gear airplane, you want the elevator to be in neutral, because otherwise that wind could actually, if you had the elevator up in a nose wheel airplane, could actually push the tail of the airplane down and pivot the airplane around. But if it's a tailwheel type airplane, in a tailwheel airplane, you would want the elevator up with a headwind to expose the top of the elevator to the wind also. Push that airplane down a little more solidly on the ground. Suppose instead you had a quartering tailwind. Suppose you had a quartering tailwind. In that case, you want the aileron down on that same side, in this case the left side, again in order to expose the top of the aileron, top of the control surface to the wind. So if you have a quartering tailwind from the left, you want the left aileron down, and in any case, tailwheel or tricycle gear airplane, you would want the elevator down so that the top of the elevator surface is exposed to that tailwind. Now, you need to know that if you have a nose wheel type, a tricycle type high wing airplane, the most critical wind when taxiing a nose wheel equipped high wing airplane is a quartering tailwind. A quartering tailwind tends to pick up the tail of the airplane and nose the airplane over. Take a look now at figure 9, and let's talk about the wind around an airplane in figure 9 and talk about how we're going to hold those control surfaces. Take a look first of all. Let's assume the wind in figure 9 is from area alpha, coming from direction alpha. In that case, what we have is a left quartering headwind. The left aileron should be held high. The left aileron should be up so that the top of the left aileron is exposed to that wind. If it is a tricycle gear airplane, a nose wheel type airplane, how should the elevator be held? Neutral if it's a nose wheel type airplane, but if it's a tail dragger, a tail wheel airplane, how do you want the elevator then? Then you want the elevator up to get the top of that surface exposed to the wind. Let's assume that you've got the wind coming from area B. Area B, how do we want the right aileron to be? We want the right aileron up. How do we want the elevator to be? Neutral elevator for tricycle gear, up for a tailwind. Suppose up for a tail dragger, up for a tailwheel airplane. Suppose the wind is from area Charlie. We've got a quartering tailwind from the left in this case. The left aileron should be held how? Down, so that the top of the aileron is exposed to the wind. And how should the elevator be? Down, regardless of what kind of aircraft you've got, regardless of nose wheel or tail wheel. And if the wind is from the right-hand side, area delta, right quartering tailwind, how do you want the right aileron held? Down to expose the top of it. How do you want the elevator held? Down for all airplanes. And you are now in great shape for flight. Well, that's certainly a bird's eye look at the weather. Let's explore some weather information together. And the first thing we want to talk about is the concept of a standard atmosphere. Standard atmosphere helps us in evaluating weather and also in figuring out aircraft performance. Now, you need to know that standard temperature at sea level is defined as 15 degrees Celsius, 15 degrees C, or 59 degrees Fahrenheit. You need to know that, and you don't have any place to look it up on the test. Now, in regard to measuring pressure, I think Galileo was the first one to measure atmospheric pressure by putting a tube into a dish of mercury. But you need to know that standard pressure at sea level is 29.92 inches of mercury. Or, if you want to measure it another way, in millibars, that equates to 1013.2 millibars, measurement that scientists use and also that they use in Europe. And again, you need to know that for the test. Now, the FAA also wants you to know that every physical process of weather is accompanied by or is the result of a heat exchange. For instance, the air gets hot over hot ground, that heated air rises, moisture condenses out and releases the heat of condensation. You get a cycle going here of the air moving around and a heat exchange taking place, and every physical process of weather is either accompanied by a heat exchange like that or it's caused by it. Now, unequal heating of the Earth's surface is what causes the variations in altimeter settings and gives us the high and the low pressure areas. And that causes our wind. So what is happening with the high and the low pressure areas? The air is moving out of a high pressure area and into basically a low pressure area. Now, near the ground, the air tries to move pretty much direct from the high to the low pressure area, and it does it pretty well because the frictional effect of that air passing close to the ground keeps it going pretty much straight, close to the ground between the high and the low pressure area. But as the winds aloft don't move directly like that. The winds aloft are affected by the rotation of the Earth, and so the winds aloft kind of curve, and they end up not really going quite straight. They curve clockwise around the highs and counterclockwise around the lows, and that gives us an angle, a difference in direction between the winds aloft, which are kind of curving around the highs and lows, and the surface winds, which move pretty much direct from the highs and the lows. And that difference in direction between the winds aloft and winds on the ground is caused by friction between the wind and the surface. Now, when you have different air masses with different temperature characteristics, different moisture characteristics, the boundary between those air masses is called a front. Here we've got a low pressure system. The air is moving counterclockwise around it. Trailing out of it to the southwest is a cold front, the boundary between cold air moving down to the southeast and warm air in front of it. Now, I know that that's a cold front because of the symbols on it. I think of those like nice cold icicles hanging off of it, and they point in the direction towards which the cold air is moving. Over here, coming out of the low pressure system and coming down to the southeast, is a warm front. That's the leading edge of a mass of warm air which is moving up to the northeast. And I know it's a warm front because it's got nice sunny looking half suns on it, and they point in the direction towards which the warm air is moving. Notice that as the air goes counterclockwise around this low pressure system, when it crosses the frontal boundary here, there is a shift in the wind direction. One of the things that always happens when you cross a front is a change in the wind direction. Now, to us as pilots, one of the things that we most easily recognize as what the FAA calls a discontinuity or a difference across the front is temperature. For a pilot, it's very easy to recognize the temperature change when you move from the cold air to the warm air or vice versa. Now, clouds are divided into families. They're actually divided into 4 families according to the height range of the clouds. Low altitude, medium altitude, high altitude, and clouds with extensive vertical development, which is your cumulus and cumulonimbus clouds, divided according to the height range. Now, when you have the suffix nimbus attached onto the end of a cloud name like cumulonimbus, what that means is a rain cloud. The word nimbus means rain. The amount of water vapor that the air can hold depends on the temperature of the air. The warmer the air is, the more water vapor it can hold in it. The colder it is, the less. Now, moisture can be added to unsaturated air by 2 processes, by evaporation and also by sublimation. Let's talk about that. If you've got water vapor in the air, and that water vapor goes to the liquid state, by definition it condenses. And when it condenses, meaning goes to the liquid state, it will form clouds or fog or dew. If the liquid, on the other hand, goes to the gaseous state, that is evaporation. Clouds, fog, or dew, whatever, becomes simply water vapor in the air. It evaporates. Sometimes, however, the water vapor in the air does not condense and become liquid. Sometimes it goes directly to the frozen state and becomes solid, ice, frost, something like that. That process, skipping the liquid state, is called sublimation. It is also called sublimation if it goes the other way, from the solid or ice form or frost directly into water vapor without become liquid in between. So you can add moisture to the air either by sublimation or by evaporation. Dew point is the temperature to which the air has to be cooled in order to become saturated. Now, when the temperature gets down to the dew point, you do not necessarily get clouds, fog, or dew. It depends on how cold the dew point is. Clouds, fog, or dew will form if the dew point is above freezing and the gas in the air condenses to the liquid state. But suppose that the gas sublimates instead because the dew point's below freezing and goes to frost. Then you would not get clouds, fog, or dew. So what you can say about when you will always get clouds, fog, or dew is when water vapor condenses. If the temperature and dew point spread, the spread between the temperature and the saturation point of the air is small and decreasing, getting closer together, that's a likely indication to you that fog or low clouds are likely to develop, and you keep your eye on that to have an idea about the likelihood of fog forming. Now, you can use the temperature and the dew point to calculate the altitude of the base of cumulus clouds. And the way you do that is the temperature and the dew point, as you go to higher altitude, converge. They get closer together at a certain rate, which is 4.4 degrees Fahrenheit per 1,000 feet. So you can figure where the base of the cumulus clouds will be by taking the spread between the temperature and the dew point at the surface and dividing by 4.4. For example, let's assume the FAA says to you that the surface air temperature is 82 degrees Fahrenheit and the dew point is 38 degrees Fahrenheit, and they want to know what the altitude is of the base of the cumulus clouds. To find that out, what you do is you take the difference between the temperature of 82 and the dew point of 38. The difference is 44 degrees, and you divide that by 4.4 because they get closer together at the rate of 4.4 degrees per 1,000 feet. 44 divided by 4.4 is 10, and 10 is how many thousands of feet the base of the clouds will be above the ground. So you multiply that by 1,000 to get it into feet, and the base of the clouds will be 10,000 feet above ground level. Now that's above ground level, but suppose you want to know where the base of the clouds will be above sea level. For that, you also need to know the airport elevation. Suppose that the FAA says to you the temperature is 70 degrees and the dew point is 48 degrees, and they want to know if the airport elevation is 1,000 feet, where will the base of the clouds be above sea level? First thing you do is take the spread between the temperature and the dew point. 70 minus 48 is a spread of 22 degrees. And you divide that by what number? 4.4. You got it. And that gives you 5. And 5 times 1,000 is how many thousands of feet above the ground the base of the clouds will be, which is what? 5,000 feet above the ground. You've got that. But the FAA in this case wants to know where it's going to be above sea level. And for that, we have to add in the airport elevation, which they'll tell you is 1,000 feet. So the clouds are 5,000 feet above the ground, and the airport elevation is 1,000 feet. 5,000 plus 1,000 means the base of the clouds will be 6,000 feet MSL. Nothing to it. You got it. Now, whether the atmosphere is stable or unstable has a very significant effect on what kind of clouds and what kind of weather you're going to get. So how do you measure whether the atmosphere is stable or not? In the standard atmosphere, temperature decreases at a standard rate as you go up to altitude, 2 degrees Celsius per 1,000 feet, although you don't need to know that for the test. If the air is unstable, it means that it gets cold much more rapidly with altitude than normal. On the other hand, if the air is stable, stable air may actually get warmer with altitude instead of colder, or if it gets colder at a slower rate than in a normal or standard atmosphere. So the way you tell whether the atmosphere is stable or not is to compare the actual lapse rate with the standard lapse rate. Now let's assume that we have moist, stable air and it's flowing upslope. If we have moist, stable air flowing upslope, what kind of weather are we going to get? Stable air resists rising. You can start it up, but it's going to quit rising as soon as it can. So when that air starts moving up, if it's moist, moisture will condense out and form clouds, but as soon as it gets to the top of that mountain ridge, the air is going to level off, stay even, and you have flat stratus-type clouds, not much vertical development. The weather that goes along with stable air is stratiform or stratus-type clouds. If there's precipitation, it's steady precipitation, and the air tends to be smooth with very little turbulence. Now, if you took that air and you warmed it from below, warming the air from below decreases the stability of an air mass and tends to give you clouds with a lot of vertical development. That rising air will carry away pollution and haze and so on in the lower atmosphere, give you good visibility, but it also gives you turbulence. Moist, unstable air tends to be characterized by cumuliform clouds, towering cumulus and cumulonimbus, and a showery type of precipitation as opposed to a steady precipitation. Now, if you have unstable air and you force it up, what kind of clouds and weather are you going to get? Unstable air, once you start it up, tends to want to keep on rising. And even when it gets to the top of the mountain ridge, it will tend to keep on going up. And what you get is clouds with a lot of vertical development. And those kind of clouds tend to give you a lot of turbulence. Whenever you see towering cumulus clouds, that indicates to you that you have convective turbulence. Convection is rising air, and towering cumulus clouds tell you that you have rising air, whether it's caused, as in here, by a mountain ridge that forces the air up, or heating of the ground, or a front, or whatever it may be. Now, let's talk about structural icing on an aircraft. There are various types of structural icing that can form on the wings of an aircraft. They all require that you be flying in visible moisture. Visible moisture takes a lot of different forms. Clouds is only one. Freezing rain is another, also snow. Now, the highest accumulation of structural icing is what you find in freezing rain. With freezing rain, what basically happens to you is that you have warm air up above, cold air down below, precipitation falls from that warm air down into that cold air, gets kind of semi-frozen, keeps on falling, and gets frozen and forms an area of ice pellets. The area where it's kind of semi-frozen is the area of freezing rain. The very highest accumulation formation, and the most dangerous structural ice is what you find in freezing rain. Now, if you're standing on the surface at an airport and you've got ice pellets dropping around on the ground around you, if you've got ice pellets at the surface, what do you suppose it tells you that you have at a higher altitude? You've got freezing rain at a higher altitude because the ice pellets are those raindrops that have finished freezing, and above the ice pellets is the freezing rain. Above that, way up in the warm air, will be the rain that it all started from. Now, when you get frost on an aircraft, you get frost because the temperature of the collecting surface, the airplane in this case, is at or below the dew point, and the dew point is below freezing. If the dew point were above freezing, you'd get dew instead, but when the dew point's below freezing and the temperature of that collecting surface gets down below the dew point, then you get frost on an aircraft, and it can cause you some significant problems by destroying the lift on the aircraft wing. Want to get rid of it before you fly. Very stable air, one example of it is when the temperature actually gets warmer with altitude rather than getting colder, and that's what we call a temperature inversion. The air gets warmer with altitude rather than getting colder. That's a very stable condition, and when you have that kind of situation, below the temperature inversion layer, down in the cold air down at the bottom, you tend to have very poor visibilities due to fog, haze, low clouds, even pollution and stuff like that. But the air will tend to be relatively smooth. Poor visibility, but smooth. When you have a temperature inversion like this, you can expect wind shear if the wind speed at 2,000 to 4,000 feet above the surface is at least 25 knots. 25 knots or more, if the wind speed is that at 2,000 to 4,000 feet above the ground, you can expect to have wind shear. Now, what is wind shear? Wind shear is a rapid change in the wind direction and or the wind velocity. And when you've got a wind of at least 25 knots above that inversion layer, you're going to have a very definite wind shear condition and a lot of turbulence on the boundary layer between those two separate masses. Now, a very common way for a ground or surface-based temperature inversion to form is by terrestrial or ground radiation on a clear, still night. If you've got a clear night, the ground can radiate its heat off into space, cool down, cool the air right next to it, and that cools off the air above it and creates a temperature inversion. If you've got a wind blowing, it will mix up that air and it will keep the temperature inversion from forming. This is exactly the same process that forms radiation fog. Radiation fog forms in warm, moist air. You need enough moisture in the air for the fog to come out over flatland areas on clear, calm nights, nights with no wind. Now, another type of fog is advection fog. Advection fog, in contrast to radiation fog, needs a wind in order for it to form, and it very commonly forms when you have an air mass move inland from the coast in the winter time. In the winter, the water is actually quite a bit warmer than the land surface is going to be. So here you've got this relatively warm, moist air over the water. The wind moves it in over that cold land. When air gets colder, it cannot hold as much moisture. The moisture condenses out and forms advection fog as that air moves inland. Now, if you're operating in Arctic conditions, you might encounter a dangerous type of fog known as steam fog. What happens with steam fog is that in the winter, cold, dry air from over the land moves from the land to over the water. And in the winter, the water is quite a bit warmer than the land surface is. So moisture evaporates from the water. But that cold air from the land cannot hold much moisture, so the water condenses out. And what you get is a lot of water droplets, and that forms steam fog just above the water. Those water droplets freeze quickly, and they give you icing conditions and also low-level turbulence. Now, if you really want to talk about hazardous weather, what we need to talk about is thunderstorms, or as the FAA often calls them, cumulonimbus clouds. Now, a cumulonimbus cloud is a cumulus cloud with what? With rain coming out of it, and they have the greatest turbulence of any clouds. A hazard around thunderstorms that is invisible but definitely there and very dangerous is wind shear turbulence. Thunderstorm has enormous updrafts going into it, downdrafts coming out of it. The boundary between those up and down currents is a zone where you have very strong wind shear, very rapid changes in the wind direction and velocity, and it's a very, very dangerous hazard. Now, the most dangerous type of thunderstorms are squall line thunderstorms as opposed to air mass thunderstorms. Squall line thunderstorms are very active thunderstorms that form in a narrow band. They develop ahead of a front. They are non-frontal because they're not in the front itself, but they develop ahead of it, and they produce the most intense hazard to aircraft. Biggest hail, strongest winds, tornadoes, the most dangerous weather. And that's because they don't tend to, because they're moving so rapidly and they lean over, they don't tend to, in a sense, rain themselves out. They have a much longer life cycle, and that lets them get a lot nastier. Now, what kind of conditions do we have to have in order to form a cumulonimbus or thunderstorm cloud? Three conditions that we have to have. We need unstable air so that once it starts up, it's going to want to keep on going up. We need moist air, high humidity, so that we can have moisture condensing out and releasing more energy. And we need a lifting force, something to kick the whole thing off in the first place. Lifting from mountains, from a front, from just the sun heating the ground, whatever it may be. Now, they call it a cumulonimbus cloud until you get the lightning coming out of it. When the lightning comes out, then it graduates technically to being a thunderstorm. So one thing that is always associated with a thunderstorm is what? Lightning, because until you see it, you don't call it a thunderstorm. A thunderstorm has three basic stages that it goes through in its life cycle. The first stage, the cumulus stage, you have basically all updrafts. The storm is growing in that cumulus stage. Now, in the second stage, which is the mature stage, in the mature stage, you've gotten large particles of moisture that are now beginning to fall. They pull the air down with them so that you have downdrafts as well as updrafts. And the way you recognize the mature stage has started is precipitation begins to fall. This is when the thunderstorm is most intense and has the most danger in it. Now, the third stage is the dissipating stage of a thunderstorm. In the dissipating stage, the thunderstorm is basically run out of energy. It's pretty much all downdrafts. It's dying out, not nearly as mean as it is in the mature stage. Pretty much all the air currents are moving down and out. Now, how do we find out about hazardous weather like this? The FAA, the Flight Service Stations, put out weather advisories for us. Now, the one type of weather advisory is an AIRMET. And AIRMET stands for Airman's Meteorological Phenomenon. And AIRMETs are the less serious type of weather advisory. They're warnings of weather conditions that are particularly hazardous to light airplanes, basically to small aircraft. And AIRMETs would be put out for things like moderate turbulence at low altitudes and things like that. Much more hazardous weather advisories are SIGMETs. SIGMETs stands for Significant Meteorological Phenomenon, and those are weather warnings that are of weather that is hazardous to all aircraft, even the airliners. For instance, in this particular case, we've got a SIGMET out for occasional severe icing at certain altitudes. Severe icing, thunderstorms, that type of thing would be in a SIGMET. But the type of SIGMET that thunderstorm information is given to you in is a convective SIGMET. The way to remember that is to remember what convection is. Convection is rising air, and what's the ultimate in rising air? It's a thunderstorm. So a convective SIGMET is a warning about significant thunderstorm activity. Tornadoes, embedded thunderstorms, or hail 3/4 of an inch or greater in diameter. In this case, it's talking about a line of thunderstorms that has here hail to 1.5 inches. So hail of 3/4 of an inch or greater in diameter meets the requirement for a convective SIGMET. Now, one of the things they put them out for is embedded thunderstorms. What is an embedded thunderstorm? That's a thunderstorm that you're not going to be able to see very well. It's buried in a front. There's all kinds of massive cloud layers around it. The thunderstorm itself is obscured by these other cloud layers and cannot be seen. That's as opposed to an air mass type storm, which sits out there all by itself on a summer day and is very easy to see and avoid. Just fly around it. Embedded storms are dangerous because you can't see them, and that makes them hard to avoid. Now, we talked about wind shear around a thunderstorm. The FAA wants you to know that there are two places where you find wind shear near the ground. One of them is when you have that strong temperature inversion. You've got strong air up above, probably calm air down below. The difference, where there's sudden change in the wind direction and velocity, gives you wind shear and gives you a lot of turbulence in that area. And the other place where you find the wind shear near the ground is when you have thunderstorms. When you are near thunderstorms, you can definitely expect wind shear near the ground. Another situation that can give you turbulence, not wind shear, but turbulence, is when you're looking out at a mountain ridge and you see what we call a standing lenticular cloud. If you've got a mountain ridge and you've got a strong wind blowing across that mountain ridge, and the air is basically stable, so the air doesn't want to go up. It goes over the ridge and continues on downwind. What will happen is you'll get a series of waves. It's like a rock sticking up in a river. It creates waves in the air downwind from it for hundreds of miles downwind. The clouds themselves that mark those waves, the peak of those waves, the clouds themselves do not move, but the wind can be moving through it at 50 knots or more. Those clouds, the stationary lens-shaped cloud, are called standing lenticular clouds, and they mark a mountain wave. And a mountain wave can have extreme turbulence in it, and you should expect mountain wave turbulence whenever you have winds of 40 knots or more blowing across a mountain ridge and the air is basically stable. Now, let's talk about how the weather is actually reported to us at various airports. Let's take a look on Figure 52. Take a look in the FAA figures on Figure 52, and let's talk about the Surface Aviation Weather Reports. The Surface Aviation Weather Reports. Now, in the left-hand column of Figure 52 there, you'll find three-letter identifiers, 5 of them going down. You do not need to know the three-letter identifiers. The FAA will refer to the three-letter identifiers in the question, and you do not need to know what city that represents. Now, after the three-letter identifier, it tells you about the report. The SA stands for the Surface Aviation Weather Report and tells you that it is a normal routine observation. The last two cities, MDW and JFK, though, the letters after the identifier are RS, and RS means that we have a record specialist, special observation taken here. Now, after that, they give you the time of the observation, 1854, 1852, 1856. These are times in Zulu time. And basically, this is the 1900 weather observation. They can't take it exactly at 1900, so they take it a little bit before the hour, anywhere from 5 to 10 minutes before, but it's essentially the 1900 weather observation. Okay, let's take a look at the cloud information, because the first thing they give us after the time is the cloud information. First of all, at the top one, INK, we don't have much of a cloud problem. It says clear, CLR for clear. Now, below that, the next one for Boise says that we have clouds at 15,000 feet scattered. You add 2 zeros to the number there, 15,000 feet scattered. The third entry down has 2 cloud layers, 700 feet scattered, you add 2 zeros, and the second cloud layer is 25,000 feet scattered. Very common to have multiple cloud layers given to us there. Now, the fourth one down, MDW, gets a little bit more complicated. At MDW, the dash X means the sky is partially obscured. Partial obscuration basically means that you can't really see a very clear and definite cloud layer. It means that your upward visibility is somewhat restricted. I used to always wonder what a partial obscuration was until I got out to the Los Angeles area and saw all the smog there. That kind of explains it. After that, it says we have a measured ceiling of 700 feet overcast, OVC for overcast. So here we have, for the first time, a ceiling at the airport. A scattered layer does not constitute technically a ceiling at the airport, because a scattered layer by definition has enough holes in it that a VFR airplane is going to be able to get through and go ahead and fly. But if you have a cloud layer that is defined as broken, or it's reported as overcast, and they do not have a dash in front of it to tell you that it's a thin broken or thin overcast, then it constitutes a ceiling at the airport. But you can always recognize when they've got a ceiling because there will be a letter in front of the cloud layer. M for measured, a measured ceiling of 700 feet overcast. And the last observation, the one for JFK, really gets interesting. We have W5X, and that means we have an indefinite ceiling, 500 feet, and the X means obscured. Indefinite ceiling, 500 feet, sky obscured. Okay, how about the visibility? Let's take a look at the visibilities, and it comes right after this cloud information. For INK, the top one, the visibility is 15 miles. Okay, how about our second weather observation? The visibility there after the scattered layer is 30 miles visibility. Nice, good conditions. For our middle weather observation, the visibility there is 6 miles with haze and smoke. When the visibility gets down to 6 miles or less, they tell you what is restricting the visibility. In this case, it's being restricted by haze, and by smoke, the letter K stands for smoke. At MDW, the visibility is 1½ miles with heavy rain and fog. Don't get caught on the test by saying that that's 11 variable to 2. It's not. What they're doing is giving you a fraction, even though it looks a little bit weird, 1½ miles visibility. Now the plus for heavy goes with the rain. The plus or minus for heavy or light comes after the precipitation symbol. If you see a precipitation symbol like R for rain all by itself, it means that it's moderate precipitation. And the R plus in this case means we have heavy rain, and we also have fog. Both of those are obscuring the visibility. At the last report, the one for JFK, we have 1½ mile visibility due to fog. The visibility is restricted due to fog. Take a look back now at the report for WINK, INK, which is the top one there, and let's read all the way through it and understand everything it says. INK is the three-letter identifier, SA for the Surface Aviation Weather Report. It was physically taken at 1854, which is for the 1900 weather observation. Sky conditions were, it was clear. Visibility was 15 miles. Now, the next figure there is the altimeter setting in millibars, the pressure in millibars, but we don't have to worry about that because as pilots, we don't use it. The first two-digit number is the temperature at the airport. The second two-digit number is the dew point. So the temperature is 77 degrees, the dew point is 63 degrees. Now, what you get to next is the wind information. Normally, the wind information is a 4-digit number. In this case, it's got a little bit more. The first two digits are the wind direction to the nearest 10 degrees. The wind is from 110 degrees, and that is relative to true north. Your winds for weather purposes are always given to you relative to true north, whether it's an hourly weather observation or a winds aloft forecast. The only time you get magnetic winds is for a takeoff or landing advisory, and you get magnetic winds then because the runways are magnetic, and so you need to know exactly where the wind is from. But for weather reporting and forecasting purposes, your winds are given to you relative to true north. So the wind is from 110 degrees relative to true north. Now, normally there would only be two additional digits there, and that would be the wind velocity. In this case, a velocity of 12 knots. But we've got a little bit more information given to us here. The wind is not just 12 knots, it's 12 knots gusting to 18 knots. It's the same way some people say I talk. Now, the last digits there, the 000, are the altimeter setting. This is what you would use to put in the altimeter setting window if you were approaching or departing this airport. that altimeter setting, they have left off the first digit on it. The altimeter setting, remember, standard is 2992, so you put either a 2 or a 3 in front of the three numbers you see, whichever is going to keep it closest to standard. In this case, you put a 3 in front, so the altimeter setting here is 30 point, you have to put the decimal point in yourself, 30.00, and that would give us the altimeter setting. Okay, you know now the information that these provide. You know how to read the hourly weather observations. What we want to do now is take a look at this whole group of hourly weather observations and talk about the way the FAA is going to be asking you questions about it, the kind of information they're going to want you to dig out of these on the written exam. And the first hourly weather observation we want to take a look at is we want to go back again to MDW. Now, MDW is the second one from the bottom, and the FAA will ask you what are the sky conditions at MDW. The dash X means we have a partial what? Partial obscuration. We have a measured ceiling. How high? 700 feet overcast, OVC for overcast. And what's the visibility? 1 1/2 miles visibility due to heavy rain and fog. R plus for heavy rain and F for fog. Okay, the FAA will also ask you which stations are reporting VFR weather conditions. VFR weather is ceiling of at least 1,000 feet and visibility of at least 3 miles. So when you take a look at it, Wink was clear, Boise was just scattered, Los Angeles was just scattered, MDW had a measured ceiling of 700 overcast, that's less than 1,000 feet, and JFK had an indefinite ceiling of 500 feet obscured, so that's less than 1,000 feet, and in both of those we are reporting less than VFR conditions. Now, as far as visibility is concerned, that's ceiling. How about visibility? At Wink, it's 15 miles. At Boise, it's 30. At Los Angeles, it's 6, which is still better than the VFR visibility of 3 miles. MDW and JFK, we've got 1.5 miles, and we've got 1/2 mile. So MDW and JFK are not reporting VFR conditions, but all of the other stations are. Now, they'll ask you at JFK, what is the wind direction and the wind velocity? JFK, the bottom one, you're looking for the 4-digit grouping. That's where your wind is. The wind is from what direction? 180 degrees relative to true north. And what is the velocity of the wind? 4 knots. The first 2 digits are the wind direction to the nearest 10 degrees. The last 2 digits are the wind velocity. Or they'll ask you, what are at Wink, INK, what are the wind conditions? And at Wink, we looked at that a minute ago. The wind conditions are from what direction? 110 degrees. And what's the velocity there? You got it, 12 gusting to 18 knots, just like I taught. Okay. They will also ask you about remarks at the end, and if you take a look at the end of the MDW report, we've got some remarks at the very end. On MDW, at the end of that observation, it says RF2, RB12. The R stands for rain, F stands for fog, and the 2 stands for 2/10. Rain and fog are obscuring 2/10 of the sky. And in the second part of it, R again for rain, B began. Rain began at 12 minutes after the previous hour. That can't have been 12 minutes after this hour because this is not a forecast, this is an observation. It has to be 12 minutes after the previous hour. So if this is the 1900 Zulu weather observation, which it basically is, a little bit before the hour, but not too much before, what time did the rain begin? The rain would have begun at 1812 Zulu. Rain and fog are covering 2/10 of the sky. Rain began at 12 minutes after the previous hour. This is basically the 1900 Zulu observation. So the rain began at what time? The rain began at 1812 Zulu. Okay, that is actual weather for an individual airport. What if you want a forecast instead? Take a look on the same page at Figure 53. Figure 53 is a page of terminal forecasts, and the whole purpose of the terminal forecast is to give you your primary information regarding the expected weather at your destination and at your estimated time of arrival. It is a forecast as opposed to actual weather information, and the primary source of weather information for your destination airport. Let's take a look down on that at OKC, which is Oklahoma City, and let's read that terminal forecast. A lot of abbreviations in it. FT stands for terminal forecast. A little bit backwards, but that's the way it goes. The next grouping of the 6 digits there is, first of all, the day of the month. 01 is the day of the month it's valid on. The center 2 digits are the starting time in Zulu, 1500 Zulu, and the last 2 digits are the ending time in Zulu, 1500 Zulu, on the next day of the month. And normally, a terminal forecast will cover 24 hours like this. Okay, beginning with the valid time, which is 1500 Zulu on the first day of the month, they are forecasting a ceiling of 1,200 feet broken. Add 2 zeros to the 1, 2. Now notice a C here for ceiling. They can't measure it, they can't estimate it because it hasn't happened yet. They're just expecting it to happen, so they put the letter C in front of a forecast ceiling. 1,200 broken, 14,000 feet broken. Very commonly there will be multiple layer of clouds, and that's the case in this particular situation. Okay, 1,200 broken, 14,000 feet broken. Then they've got the wind. Wind is from 180 degrees at 15 knots, gusting to 28. And then they say that the layer is broken, variable to scattered. In other words, the broken clouds are sometimes variable to scattered. Okay, then we get to a period, and that period means that that's the end of the information for that particular time frame. We get another time. It's whenever you see a new time, in your mind, put in the word by, because what it's saying is by 1800 Zulu, this is what the weather should now be. So by 1800 Zulu, they're forecasting a ceiling of 3,000 feet broken and another cloud layer at 25,000 feet broken. And let's see on the second line what else they've got to tell us. The wind is going to be from 230 degrees at 15 knots, gusting to 25 knots, and that lower broken layer will occasionally be scattered. But they're also forecasting a chance of ceiling 700, sky obscured, 1/2 mile visibility in TRW, which is thunderstorms and heavy rain showers with wind gusts to 40 knots. Not particularly pleasant weather. A period, so that's the end of a time frame. By 2100 Zulu, we should have CFP, which stands for cold front passage. Now, when we were talking about fronts, what's one of the things, in addition to temperature, that we said was going to change when you had a front go through? The wind direction. So we should get a wind shift here. Cold front passage. With a cold front passage, they're forecasting 10,000 foot scattered, ceiling of 25,000 feet broken. And then on the third line, let's see what else we've got to find out here. Wind from 330 degrees at 15 knots, gusting to 25 knots, with a chance of ceiling 3,000 feet broken, 5 miles visibility in thunderstorms and light rain showers. T for thunderstorms, RW dash for light rain showers. And a period, and so that's the end of that time frame. And then it says by 0200 Zulu, we're forecasting weather of 10,000 foot scattered clouds, an additional layer at 25,000 feet scattered. The wind in that time period should be from 350 degrees at 15 knots, gusting to 25 knots. A period, so that's the end of that time frame. Now, the very end of this, starting by 0900 Zulu, is what the FAA calls the outlook period. The terminal forecast covers 24 hours. But 24 hours in the future is a long way in the future for the FAA to let themselves get pinned down on exact ceilings and visibilities. So during the end of this, the 6 hours at the end, they call it the outlook period, and all they give you is a general idea. Is the weather going to be VFR? Is it going to be marginal VFR? Is it going to be IFR? If it's going to be marginal VFR or IFR, why? Is it due to ceilings, visibilities, or what? And roughly, what is the wind going to be? Okay, by 09 Zulu, the beginning of the outlook period, they're forecasting VFR weather conditions and they're forecasting wind. Now, As far as the weather conditions are concerned, IFR is ceiling less than 1,000 feet and or visibility less than 3 miles. If it said marginal VFR, that would be a ceiling between 1 and 3,000 feet and visibilities of 3 to 5 miles. VFR means ceilings of better than 3,000 feet and or visibilities of 6 miles or better. If it says wind here, it means that the wind is going to be 25 knots or greater. So in this particular case, we're looking at VFR weather conditions, but they do expect it to be windy. Alrighty, let's look at some other questions that the FAA is going to ask you on the test. Take a look first of all at Tulsa, the very last terminal forecast, TUL for Tulsa. They want to know when the wind is forecast to shift at Tulsa. So when you're reading the Tulsa forecast, begins being valid on the first day of the month at 1500 Zulu, and we want to look at the wind. The wind by 1500 Zulu is forecast to be from 190 degrees at 15 knots gusting to 22. By 1900 Zulu, let's see what the wind is going to be then, from 180 degrees at 15 gusting to 20. Well, from 190 to 180 is not really much change. I wouldn't really call that a wind shift. After 2300 Zulu, though, there's our abbreviation, CFP, for cold front passage, and when you have a cold front pass, what are you probably going to get? You're probably going to get a wind shift, so let's take a look in the next line and see if that happened to us. And sure enough, in our wind information, the wind is now going to be from 320 degrees at 15 knots gusting to 25. It changed from 180 degrees to 320 degrees, which is certainly a very significant wind shift, and that happened at by 2300 Zulu when the cold front went through. So the wind's forecast to shift at Tulsa, TUL, by 2300 Zulu. Okay, let's take a look now at MLC, which is for McAllister, and let's take a look at MLC and see what they tell us about the outlook for the weather conditions is. Now, as soon as they say, what is the outlook, they're not talking in a general kind of way. What do we expect the weather to be? They mean specifically, technically, the outlook period of the terminal forecast. That's the last 6 hours, the last chunk of information. So on MLC, look at the last line of it and take a look at the very last information by 0900 Zulu, which is the outlook period. What are they expecting in the way of sky conditions? Marginal VFR conditions. And it's going to be marginal VFR due to what? Ceilings or visibilities? Which one? Ceilings. The ceilings are going to be what makes it marginal VFR, CIG for ceilings. And we know that simply because it says ceilings as opposed to visibilities. And they're also expecting what kind of weather along with that? TRW for thunder showers. Thunderstorms and rain showers are thunder showers. So in the outlook period, marginal VFR conditions due to low ceilings and also thunder shower activity. Okay, take a look at PNC, Ponca City. At PNC, they want to know in the outlook period, what is the wind forecast to be? Okay, if they want the outlook period at PNC, you go to the last line and you go to the very end information. By 09 Zulu, the beginning of the outlook period, they're forecasting VFR weather conditions in regard to clouds and visibility. And what does it say about the wind? It says the word wind, and you just need to know that if they use the word wind in the outlook portion of the terminal forecast, the wind is forecast to be 25 knots or greater. In the body of the forecast, they tell you exactly what strength they expect it to be, but in the outlook portion, they put the word wind in if it's going to be 25 knots or greater, and that's the only information you get in the outlook period as far as what the wind is going to be. Take a look now at HBR, which is Hobart. HBR, which is Hobart, and the FAA will say at 1600 Zulu, what is the wind forecast to be? Alrighty, so let's start with the Hobart forecast, beginning on the first day of the month at 1500 Zulu, which is when it becomes valid. Let's take a look and see what the wind is forecast to be during that time period, from 300 degrees at 10 knots. Period, it's the end of the time frame. The next time frame says by 1700 Zulu. What time did I say the FAA wanted to know about? 1600 Zulu. So that's going to be before 1700. It's going to be the 300 degrees at 10 knots. The time frame between 1500 and 1700 includes 1600 Zulu. So the wind at Hobart at 1600 Zulu will be from 300 degrees at a velocity of 10 knots. Okay, take a look at gauge, G-A-G, take a look at gauge, and the FAA will ask you between the hours of 1600 Zulu and midnight, what is the ceiling forecast to be? So what we have to do when we get to the gauge forecast is we have to start looking for information about 1600 Zulu. Well, the first time is 1500. Let's see if that covers us like it did on the wind. So we take a look on here and we're looking for when the next time period is, but son of a gun, the next time period in the gauge forecast, GAG, is for 1600 Zulu. And they want to know what the ceiling is forecast to be. Okay, the first layer of clouds they tell us about is 6,000 feet scattered. But is a scattered layer a ceiling? No, it's not. It is not a ceiling, and notice that there's no letter C in front of it because a scattered layer does not constitute a ceiling. It's got to be broken or overcast, and on top of that, not thin. The next layer of clouds is what altitude? 10,000 feet broken, and it's got a C in front of it to tell you that this is what they're calling the ceiling. So what's the ceiling at gauge between 1600 and midnight? Ceiling is 10,000 feet broken, and that goes on until you get to the end of this time frame. Let's take a look what the next time frame is going to be on that particular one, not on this line, so we'll check on the next line, and that goes all the way until 01 Zulu. So from 1600 up until midnight, it's going to be a ceiling forecast of 10,000 feet broken. Alrighty, let's do some talking about winds and temperatures aloft. And on the same page, up at the top of the page, we've got figure 51, which is our winds and temperatures aloft forecast. Now, before we look at that too close, there's one thing they're going to ask you about that we do not have a sample of on that particular figure, and that is what do they do when the winds are light and variable? Winds that are light and variable are put in the winds aloft forecast as follows. They put 9900 in the winds aloft information. Where you'd expect the wind direction and velocity to be, what you get is 9900, which is simply a code that says it's light and variable. The only thing that's tricky about that is that you need to know for the FAA exam how light and variable is, and that means that the wind speed is less than 5 knots, and you need to know that. Light and variable means the wind speed is less than how much? Less than 5 knots. Okay, taking a look at figure 51, let's take a look at the information for MKC at 3,000 feet. MKC at an altitude of 3,000 feet. Just like in the terminal forecast and in the aviation weather observations, surface observations, the first 2 digits there are the direction the wind is from to the nearest 10 degrees. The second 2 digits are the wind velocity in knots, and again the direction is given to you relative to true north. So at MKC at 3,000 feet, the wind is from 050 degrees at a velocity of 7 knots. They don't bother to give the temperature there when it's that close to the ground. Notice at Denver they do not have, and several other stations here, they do not have any winds aloft given at 3,000 feet. These are MSL altitudes. The elevation at Denver is up around 5,000 feet, so you'd be 2,000 feet underground if they tried to give you winds there, and they're a little bit smarter than that. So the first one we would have for Denver would be quite a bit higher. Okay, wind at MKC is from 50 degrees at a velocity of 7 knots. Let's take a look at St. Louis, STL, at 18,000 feet. At St. Louis, come across until you get to 18,000 feet, and when you get to 18,000 feet, it says 2356 minus 16. The wind is from 230 degrees at a velocity of 56 knots, and the temperature is minus 16 degrees, and that's in degrees Celsius in degrees C. Wind direction, wind velocity, and the temperature. Okay, take a look now at Denver. Take a look at Denver at 30,000 feet. at Denver at 30,000 feet. We've got wind information given 235347. The wind is from 230 degrees at a velocity of 53 knots. And the 47 is the temperature, but what in the world happened to our temperature? Well, up at the top of the table it says that temperatures are negative above 24,000 feet. In other words, when you get above 24,000 feet, it's always going to have a minus sign in front of it. It's always going to be a negative number. And to save themselves a little bit of teletype space, they simply get rid of the minus sign. You're at 30,000, you're well above 24, so by that you know that the temperature is minus 47 degrees, even though the minus sign has been left out. Let's assume they get a real strong wind. Let's assume they get a wind in excess of 100 knots. One of the problems they've got with the winds aloft forecast table is that they've only got 6 spaces allocated for doing the wind information. 2 for the direction, 2 for the velocity, and 2 for the temperature. So what happens if you get a wind velocity of more than 100 knots? How do they handle it? Well, the way they handle it is they play games with it. And let's take a look at how they play the games with it. What they do is they take the wind speed and subtract 100 knots from it. That will fit the wind speed into a 2-digit space. To tell you that they did that, they take the wind direction, the 2 digits that are the wind direction to the nearest 10 degrees, and they add 50 to it. What that does is give you a wind direction that's impossible, that doesn't exist, and that's their way of tipping you off that the wind velocity is actually 100 knots stronger than it looks like, because it makes a big difference to you whether the wind is 30 knots or 130 knots. And this is their way of making everything fit in the table and doing it and letting you know about it as long as you remember it. And you do need to remember it for the written exam. So let's take a look at St. Louis at 34,000 feet and see what happens to us here. St. Louis at 34,000 feet, that's the last entry in the 34,000 foot column. When you look at it, what it looks like is that the wind direction is from 730 degrees at a velocity of 6 knots and a temperature of minus 49 degrees. Well, first of all, there's no such wind direction as 730 degrees. And it would also be very strange to have a wind of only 6 knots up at 34,000 feet. So those two together are your tip-offs that something is funny. So in order to convert this and to figure out exactly what's going on, first of all, the temperature we got no problem with. It's 49 degrees minus 49 degrees. That part of it has not been played around with and we're okay. What we have to do is decode the 7306, and here is exactly how we do it. What we do is we take the first 2 digits, which are the wind direction, the 73, and we subtract 50 from them, and that gives us a actual wind direction of from 230 degrees. We know to subtract 50 because we just remember that, and because 730 degrees, there is no such direction for a wind. So our actual wind direction is from 230 degrees. Because they played games with the wind direction, that told us automatically that we needed, that the wind was actually 100 knots stronger than it looks like it is. So to the 06 that's in the table, we add 100, and the actual wind velocity is 106 knots. The wind direction is from 230 degrees, and the wind velocity is 106 knots. See? Nothing to it. Not as long as you know the tricks. Let's assume that you want to know the forecast for a big general area. Makes your flight a lot safer rather than just a specific airport. If you want to know that, you need an area forecast, and for that, take a look at Figure 50. Figure 50 is the area forecast, and the whole purpose of an area forecast is to determine forecast weather conditions between weather reporting stations. In other words, you got actual reports an actual forecast for individual airports, weather stations, but you want to know about the en route part of the trip. So that's what you use the area forecast for, to determine the weather, forecast weather between weather reporting stations. And among other things, it tells you the freezing level and the areas of probable icing aloft, where you would run into icing conditions and what the freezing level is. Now, it starts off up at the top of it with a section called hazards. And what it will do then in the hazards and flight precautions section is it will tell you what areas on here have hazards that meet what they call the in-flight advisory criteria. They tell you about hazards like turbulence and icing, and they also tell you about thunderstorms that are forecast to be at least scattered in coverage. So they'll tell you about flight precautions regarding turbulence, regarding icing, regarding IFR, and if there were thunderstorms, they would have a section on that to tell you about thunderstorms forecast to be at least scattered in coverage. And as far as the turbulence is concerned here, it says you're going to have turbulence in Tennessee, Alabama, and the coastal waters. And we're going to look at that a little bit later. Now, up at the top, all it does is tell you under flight precautions what they are and where they're going to be, and the detail is then in an expanded paragraph later on. So let's move down here and take a look. There didn't happen to be any thunderstorms that were being forecast. We've got a paragraph called the synopsis that just simply gives you the big picture about what's happening as far as the weather is concerned. We've got a paragraph that they did not ask us about on this test regarding where the icing and freezing level are going to be located. And then as we go on further down on that forecast, we get into in the area forecast, we get to the turbulence section. Okay, turbulence, Tennessee, Alabama, and the coastal waters. That's where they said it was going to be. The FAA in the test will ask you what is causing the turbulence, what are you going to get, and what's causing it. The first thing they do is define where it's going to be located, from SLK to FLO to 90 south of MOB. These are all VOR stations, and what you would do then is you would plot those on a map and you'd say, okay, within this area is where the turbulence is going to be. Now, what kind of turbulence are we going to get? Starting on the left side in that paragraph again, it says occasional moderate turbulence from 25,000, you add 2 zeros, just like you would on clouds, to 38,000 feet due to the jet stream. Moderate turbulence from 25,000 to 38,000 feet due to the jet stream. As you go further on down in that area forecast, you get to a paragraph called significant clouds and weather. And this is going to describe the clouds, it's going to describe restrictions to visibility and so on. A summary of cloudiness and weather significant to flight operations, and they break it down by states or whatever else is a logical geographic area. Okay, the first thing it says under significant clouds and weather, let's take a look at the times going across there. It says valid until 4th day of the month, 2300 Zulu, but then we've got an outlook, and the outlook period is from 2300 on the 4th day of the month until the 5th day of the month at 0500 Zulu. And remember to watch on the FAA questions, because this can get very tricky, whether they're talking about the outlook period or not. If they say, what is the outlook for, they're not asking you what is the weather supposed to be, they're asking you in the outlook time period, what should the weather be. So whenever they use the word outlook, they're using it very specifically to indicate the ending period of the forecast for the specific outlook. Okay, we've got our outlook period down. Let's take a look back and see what else they say. First of all, they say during the main body of the area forecast, we're going to have IFR weather conditions in Texas. Let's take a look at what they say. From SAT, these are VOR stations in Texas, to FSX, to BRO, to MOV, back to SAT. What we're going to have is visibilities below 3 miles in fog till 1500 Zulu. Visibilities less than 3 miles are IFR weather conditions, and so that part of Texas will be IFR till 1500 Zulu. Now the rest of it, Oklahoma, Arkansas, Texas, Louisiana, Mississippi, Alabama, and the coastal waters. What are we going to have in that area? 8,000 foot scattered clouds, variable to clear, except visibilities below 3 miles in fog till 1500 zero over portions of south central Texas, which they just told us about before. So really the only area with bad weather is going to be south central Texas. The outlook is going to be for what conditions? VFR conditions. When we get to Tennessee, TN for Tennessee, it says we're going to have ceilings of 3,000 to 5,000 feet broken, 10,000 feet, with visibilities occasionally 3 to 5 miles in fog, becoming above ground level 4,000 to 5,000 feet scattered, to clear by 1900 Zulu. And the outlook in Tennessee is for VFR weather conditions. Okay, so what's the FAA going to ask you about this? They're going to say to you, what is the obstruction division forecast between 1040 Zulu and 2300 Zulu for all of the area except Tennessee? Well, when they stop it at 2300, they're stopping it just before the outlook period, and they're asking for everything except Tennessee. So what they're looking at is this section here, and it says we're going to have basically clouds 8,000 feet scattered to clear, except that the visibilities will be below 3 miles in fog till 1500 Zulu, basically in south central Texas. So scattered, 8,000 foot scattered to clear, except visibilities below 3 miles in fog over south central Texas area. Now the outlook period here is from 2300 Zulu through 0500 Zulu. VFR means the same thing here that it means in the terminal forecast. VFR means a ceiling greater than 3,000 feet and visibilities greater than 5 statute miles. Visibility 3 to 5, ceilings of 1,000 to 3,000 feet is marginal VFR conditions. Okay, so what do we have in the outlook period or obstructions division from 2300 to 0500 for the entire area? Well, the thing that's tricky about this is if you look in the significant clouds and weather information, the very first paragraph you see there says IFR in Texas, but that is in the body part of the area forecast, not in the outlook period. Because when you get down here to where it says outlook the first time, it says outlook VFR conditions, and for Tennessee it also says outlook VFR conditions. So during the outlook period, which is after 2300 Zulu, what weather conditions are they forecasting in the whole area? They're forecasting VFR weather conditions with no obstructions division, no cloud problems of any significance, and VFR is forecast there. Just be very careful that you understand what the FAA is actually asking. Take a look now on Figure 54. Take a look on Figure 54, which is the weather depiction chart. The weather depiction chart, the purpose of this is to determine the general weather conditions so that you can base your flight planning on it. Now, when you look at that weather depiction chart, one of the things you'll notice is that in some areas there is a line around the weather, and then in other areas you've got a line with hatching through it. If there's no line at all, like there is through most all of the western half of the country, it means that you have VFR weather conditions. Now, this is an actual chart. This is not a forecast. VFR weather conditions observed. The line without the hatching in it means that we have observed marginal VFR conditions, and the contour line with the hatching inside it means that we have observed IFR conditions. And again, we're using the same definitions on all of these charts and forecast, observations and forecasts. Take a look in central Arkansas. We have a station circle there in central Arkansas, and you'll notice that that station circle is partly shaded in. If the station circle is all the way filled in, if it's solid, it means that they have overcast conditions. If it's partly filled in, it means we have broken clouds, and if only a quarter of it is filled in, it means then that we have got scattered clouds at that particular station. The height of the clouds is given underneath the station circle, and you add 2 zeros to it just like you would to the other cloud heights. Visibility, if any, if there's any restriction to the visibility, will be given out to the left of the station circle. So let's assume they say that you're flying from central Arkansas to southeast Alabama, and you want to know what the weather conditions are. Central Arkansas, the station circle is 3/4 shaded in, so we've got broken clouds there, but they're pretty high. How high are those clouds? 25,000 feet, 25,000 foot scattered clouds. Okay, in Mississippi, we've got a quarter filled in, so what we've got there is scattered clouds, and again at 25,000 feet. And when you get down into southeastern Alabama, 1/4 filled in means we have scattered clouds, and what's the height of the clouds there? Still 25,000 feet. So going from central Arkansas over into Alabama, you're going to have scattered clouds at what altitude? 25,000 feet. Take a look now in eastern Texas. In eastern Texas, we've got an area with a contour line and hatching across it, and that means that there, inside there where the hatching is that marginal VFR or IFR weather conditions. IFR because we've got the contour line with the hatching, and by the way, the contour lines are explained in the legend in the lower right-hand area of that chart. So we've got IFR weather conditions in Texas, and now the eastern Texas, and the FAA wants to know what it's due to. Well, when you take a look at the station circle, the X through it means the sky is obscured. Out to the left is the visibility, which is 2 miles, and what looks like an equal sign between the visibility and the station circle tells you that they are experiencing fog. That's the restriction to visibility, which in this case is fog. So we've got visibilities there of 2 miles due to fog. So what's causing the IFR weather here in eastern Texas is fog. It's due to fog. Now there is a front to the north of there. There's a front going from New Mexico through into Indiana. And when you look at that front, one of the things that you'll notice about it is it's got both kinds of frontal symbols. It's got these sharp, pointy icicle things hanging down to the south, and these nice, warm, half-sun looking sunny things pointing up to the north. What that means is we have a stationary front. We've got warm air pushing north, stopped right here. We've got cold air pushing south, stopped right here. We've got a frontal boundary right here with the warm air and the cold air pushing against each other, and neither one has overpowered the other yet. So that front is stationary, and it helps to think of those as frontal symbols as pulling against each other and basically giving you a stalemate. We've got a stationary front. Take a look now on the coast of Oregon and California. On the coast of Oregon and California, we've got some IFR weather conditions. There's our contour line with a hatching, and we want to know why we have IFR weather conditions. Well, the station circle, the one up in Oregon, is filled in, so we have overcast. The height of the ceiling is underneath it. The 3 stands for 300 feet. The visibility there, however, is 5 miles, and 5 miles is much better than IFR visibility. IFR visibility is less than 3. So we got 5 miles visibility with drizzle. Those two things that look like commas mean that we have drizzle. Down in Northern California on the coast, we have a sky obscured. The 2 underneath it means that we have a 200-foot ceiling, and the visibility out to the left is 1 mile visibility due to fog. We've got those lines that stand for fog again. So here the visibility is pretty bad, but up in Oregon the visibility was pretty good relatively, 5 miles, certainly better than IFR. So what is the consistent thing, the ceiling or the visibility, that makes the weather IFR? The ceiling, it's caused by low ceilings in Oregon and California, is why we have our IFR weather there. Now the weather depiction chart is an actual chart, but if you want a forecast chart of the entire country, what you go for there is the low-level prognostic charts, the low-level prognostic charts in figure 55. So take a look at figure 55. Now you've got 4 charts on there. Here's how they're broken down. The 2 charts on the left-hand side of the page are a 12-hour forecast. They give you information for 12 hours in the future. The 2 charts on the right-hand side of the page are a 24-hour forecast. The charts up on the top, the 2 top charts, give you information about clouds, turbulence, and freezing levels, and the 2 charts on the bottom of the page give you information about frontal positions, precipitation, movement of pressure areas, and things like that. So these 2 charts, the top one, by the way, is the significant weather prog, and the bottom one is the surface prog. These 2 charts provide analysis of forecast frontal positions, frontal activity, cloud coverage and areas of precipitation, along with some information on turbulence. Now, you will not have any other legend to this chart other than what you see on the page. But if you take a look right in the center between the top two charts, you will see some very useful information. And when you zoom in on that information between the two charts there, it tells you what the lines on here mean. A smooth line means IFR weather. Ceilings less than 1,000 feet and or visibility less than 3 miles. If there's a scalloped line, that's marginal VFR that the scalloped line is enclosing. Ceilings of 1,000 to 3,000 feet and or visibility 3 to 5 miles. If there's a dashed line around an area, they're talking about moderate or greater turbulence. And if there's kind of a small dashed line, that's the freezing level above mean sea level. In other words, what the altitude of the freezing level is. Now, what the FAA will do is give you questions like this. They will say, what is the forecast weather for the Gulf Coast just ahead of the front during the first 12 hours? The first trick is you've got to know that the two left-hand charts are the two that have to do with the 12-hour period. So what you need is to look at the two left-hand charts. Now, on the first left-hand chart, the lower left one, which is the surface Prague, you see the front, the cold front, going down through eastern Texas. And here's the Gulf area along from Texas and on into Louisiana. In front of the cold front, there is an area of precipitation forecast, and that precipitation is thunderstorms. The R with a kind of arrow on it stands for thunderstorms, and also rain showers. There's a triangle there with kind of a dot on top, or at least it should have a dot on top, for rain showers. So they're forecasting thunderstorms and rain showers in front of the cold front. Now, how about whether it's going to be VFR, marginal VFR, or IFR? Well, if you take a look at the chart above there, which is the significant weather Prague, that's the one that tells you about IFR and marginal VFR. And the cold front ran right along about through here, so we have a scalloped line area in eastern Texas towards the Gulf Coast. That's marginal VFR weather forecast. And then the solid line over here is talking about IFR weather conditions, and that touches the Gulf Coast around Louisiana. So what we've got is marginal VFR and IFR weather conditions forecast, along with thunderstorms and rain showers, and that's the weather that's forecast for the Gulf Coast ahead of the front during the 12-hour period. Okay, suppose they said to you, take a look at the band of IFR weather in the western states and which way is it supposed to move. The IFR weather in the western states is this weather here over basically southwestern Montana down through Idaho, western Wyoming, and so on. That is an area of IFR weather, and we know that by looking at the chart above where it had the solid line around it. The type of precipitation in there is continuous snow. An asterisk stands for snow, two of them stand for continuous snow, and the arrow here pointing to the east with a 30 on it tells you which way that area is moving and at what velocity. Which way is the area moving? It's moving east. How fast? 30 knots, moving east at 30 knots, and it has continuous snow inside that area. Take a look now in Lower California, but take a look on the 12-hour significant weather Prague. On the 12-hour significant weather Prague, we want to know what kind of weather is forecast in Lower California. When you get there, you find a dashed broken line around California, and the legend in the middle tells you that that means we have an area of forecast turbulence. Now, what kind of turbulence is forecast? That single little mountain peak in there means we're talking about moderate turbulence. If they were talking about severe turbulence, that little mountain peak symbol would have a double cap on it, kind of like a mountain wave, kind of like a lenticular cloud sitting on it. Okay, so we're talking about forecasting moderate turbulence. What altitude? Well, think of the line in that area under the 180. The line is representing the weather itself, in this case the turbulence. Whatever altitude is on top of the line is the top of the weather. You add 2 zeros to it, and the top of the turbulence is 18,000 feet. Whatever altitude, if any, is under the line is the base of the weather. In this case, there isn't any altitude under the line, so where does the turbulence go down to? To the surface. They're forecasting moderate turbulence from the surface up to 18,000 feet. Now, take a look on the 24-hour significant weather prog, which is the upper right-hand chart, and take a look in southeastern Oklahoma. Here's Oklahoma, here's southeastern Oklahoma, and the FAA will ask you what the freezing level is in southeastern Oklahoma. These dashed lines represent the freezing level. We've got one going through basically the northeast part of the state and one of them just barely nicking the southeast corner. And if you follow these lines on up to the upper right-hand part of the chart, you'll find out what altitudes those freezing levels are actually located at. And the top freezing level line is 8,000 feet. The bottom freezing level line is for 12,000 feet. And the question is, where is the freezing level located in southeastern Oklahoma? Well, when you take a look back at southeastern Oklahoma, neither one of those lines really runs through southeastern Oklahoma. The FAA, in fact, may have been looking and thinking about the 12-hour prog, because on the 12-hour prog, the 12,000-foot freezing level line goes right smack dab through southeastern Oklahoma, although on our particular chart that they sent us to, the 24-hour prog, it doesn't exactly go through there. I would say that 12,000 is still going to be the best answer. I think that's what the FAA is looking for on the written exam. Freezing level, southeastern Oklahoma, pretty close to 12,000 feet. Now, another way to get weather information is from pilot reports. As you fly, you are strongly encouraged to give flight service reports about what's going on. And if you take a look on Figure 57, you'll find a sample of a pilot report on Figure 57. And the pilot reports are divided into sections, and each section is identified with a two-letter label. Let's take a look at what the information this pilot gave us. First of all, UA stands for a pilot report. Now, how they get pilot report out of that, I don't know. Maybe UA really stands for the unreliable airman. But regardless, the pilot was reporting over, OV for over, a route from OKC to TUL, which happens to be Oklahoma City to Tulsa. Okay, TM is the time of the pilot report, 1800 Zulu. FL is flight level, and this will be his altitude, and you add 2 zeros to it. His altitude was 12,000 feet. TP is type of aircraft. He was a BE-90, which is a Beechcraft, a Beech 90. Okay, then we've got SK for sky conditions. Sky conditions are, first of all, we've got bases of clouds reported at 1,200 feet broken with the tops of those same clouds at 5,500 feet. We know that it's bases because it comes in front of the cloud contraction. The tops come after the cloud contraction. The interesting thing about these bases, because they're reported by a pilot, they're given to us relative to mean sea level, MSL, not above ground level. When you're flying an airplane, when you look at your altimeter and tell the controller an altitude, you're looking at your altimeter in regard to how you are relative to sea level. So pilot reports of both cloud bases as well as tops are given relative to mean sea level. Now, the FAA is going to come along and they're going to throw at you a question like this. What is that cloud base like relative to an AGL number? Where is it above ground level if the airport elevation is a certain elevation? For instance, 614 feet. Okay, the airport elevation is 614 feet. A pilot on takeoff reported bases of the clouds at 1,200 feet. But the point is that the bases reported by the pilot are given to you above sea level, not above ground level. If you want to know where those clouds are above ground level, above the surface, you would have to subtract the airport elevation. The FAA tells you in the question the airport elevation is 614 feet. So you take the base of the clouds in MSL as reported by the pilot, subtract the airport elevation, which will be given in the test question, and the difference will be how high the clouds are above the airport, above the ground, and in this case 1,200 minus 614 comes out to clouds being 586 feet above ground level, 586 above ground level. Okay, that's one layer of clouds that the pilot reported, but what else did the pilot report as far as the clouds are concerned? Well, after that broken layer, there's a slash. We've got some more cloud information coming up. So go back to the beginning of the second line, and the next cloud layer has bases of 7,200 overcast and tops at 8,900 feet. Bases of 7,200 feet, tops of 8,900 feet. We've got a slash, and then it says clear above. That sounds pretty good. TA stands for temperature. The temperature there is -9 degrees, and that's Celsius. Temperatures are always in Celsius aloft. WV stands for wind velocity. That wind it's actually more than just the velocity. You could say it's the wind direction and velocity. It's from 090 degrees relative to true north, and the wind velocity is 21 knots. And TB stands for turbulence. They're telling us what kind of turbulence they got and where. Moderate turbulence between the altitudes of 5,500 and 7,200 feet. ICG stands for icing. This particular pilot reported some structural icing conditions, light to moderate icing, and it was clear type icing as opposed to rime icing, and he found that between 7,200 and 8,900 feet. A pilot report simply giving us another way of figuring out what the weather is. Very useful to other aircraft. Now, we've talked about thunderstorms, but we have not talked about how to find out information about thunderstorms. One way is what they call a radar weather report. There is a radar weather report that actually goes out over the teletype, and the radar weather report, the flight service guy will read to you. There's simply a coded report that tells you the location of the precipitation along with the type of it, how heavy it is, the intensity of it, and the trend. Where it's located, what type it is, whether it's thunderstorms, snow showers, rain showers, whatever it might be, along with the intensity, is it strong or weak, and the trend, is it getting stronger or weaker? And this is the radar weather report, simply a teletype report. Probably the more commonly used, or at least the one that pilots are more familiar with, way of finding out about thunderstorms, is to take a look at the radar summary chart. And we've got one in figure 58, the radar summary chart in figure 58. Now, what the radar summary chart is, it's an actual chart, not a forecast chart, that shows lines and cells of hazardous thunderstorms, information that is not shown on other weather charts, lines and cells of hazardous thunderstorm. And by the way, I'd like to apologize for the quality of this chart, but it's exactly what you're going to get on the FAA written exam. The quality is not too good on this. Now, on the radar summary chart, what they do is they have arrows and feathers to indicate the direction and speed of movement of various radar returns. They get echoes with weather radar off of precipitation, not just clouds, but actually off of precipitation, and then they can tell you which way those radar echoes are moving and how fast they're moving. For instance, take a look at Area A. In Area A, which is basically in the, I think that's Kansas area, you'll notice there is a feather coming out of Area A going to the right. It points pretty much due east, so this area of observed precipitation, radar echoes, is moving east. A half feather on there stands for 5 knots, a full feather stands for 10, so that area is moving towards the east at a speed of 15 knots, a full feather for 10 and a half feather for 5. Now, they also use a different type of arrow, which is more for general, for a cell as opposed to a general area. Take a look at Area D. On Area D down here, you'll notice that there is an arrow with a 20 at the head of it. Again, that is representing movement of the radar echoes. This tends to be more for a cell as opposed to an area, but it's moving northeast at a velocity of how much? 20 knots, northeast at 20 knots. Now, the maximum tops of the radar returns, they can point the radar up and measure how high the radar returns are. The FAA on the test calls them maximum cloud tops, although they're really the return of the radar, which is off of precipitation, is shown by a line with 3 digits on top of it. The number on top of the line is the top of the precipitation, the echo return, or in this case, as the FAA calls it, the cloud tops. 220 means 22,000 feet, so the maximum cloud tops in this area is 22,000 feet. Now, They also give you some information about what type of precipitation is causing the echo return. And if you take a look in Area Charlie, you will notice the letters there, RWH to the left of the C, stand for rain showers, and the plus means heavy rain showers. So rain showers is what's causing the precipitation activity in this area. Sometimes they'll tell you it's snow, sometimes they'll say it's thunderstorms. In this case, it happens to be only heavy rain showers. Now, when the weather really gets nasty, they show weather watch areas on this chart. Weather watch areas are enclosed by dashed lines, and the purpose of the dashed line, the weather watch area around Area Bravo here, is to tell you about areas where they have tornadoes or severe thunderstorms forecast. Tornadoes or severe thunderstorms forecast. So if they ask you where is a weather watch area on the chart, Area Bravo has got one, because there is the rectangular dashed outline box where they're expecting the severe weather to occur. All kinds of weather information. How do we lay our hands on it? How do we get it? Well, the normal way that we do it is by communicating with a flight service station. Now, the flight service station is the people at the FAA who are charged with gathering and disseminating to us the information as pilots that we need in order to be able to make a safe flight. There is some information that you need to give the weather briefer at the flight service station in order for him to be able to give you a good briefing. And here's the information that the FAA wants you to tell that weather briefer. First of all, he needs to know that you're a pilot. They get calls from people for other weather purposes, so he needs to know that you are a pilot. He needs to know whether you're going VFR or IFR. Are you capable even of going IFR, or are you VFR only? It makes a difference in how he briefs you as far as the weather is concerned, what he thinks is hazardous weather for you. Give him your route, give him your destination, and give him your aircraft type. These things are very important for him to pick out what constitutes significant weather. The weather that is significant, for instance, to a Cessna 150 is going to be very different than from weather that is significant to a Boeing 727. So give him, whether you're a pilot, whether you're a VFR only pilot, your route, your destination, and the type of aircraft that you're flying. Now, there's 3 types of weather briefing that you might ask for, and you need to know these for real life as well as the test, because this is how you get your weather information. A standard briefing is what you ask for if what you need is a complete weather briefing. You've got no other weather information whatsoever, and you need a complete and total briefing. That is a standard briefing. However, sometimes you might want an abbreviated briefing. If you've already looked, for instance, at AM weather or gotten some other information on what the FAA calls a mass disseminated data, you've listened to a transcribed weather broadcast or somehow gotten some other weather information, and all you need is to fill in a few holes, what you ask for is an abbreviated briefing, basically to supplement information you've already got from another source. If you want a briefing for tonight, for a trip, say in the morning, information for a trip that is 6 or more hours in advance, then what you want is an outlook briefing. He won't bother to give you a great deal of detail because the detail will change, but what he will do is give you an overview, and that's what you want to ask for is an outlook briefing if your trip is going to be 6 or more hours in the future yet. Now, you can call the flight service station on the telephone and get this weather information. But suppose that you're en route in an aircraft and you want to get some updated weather information. You can contact flight service on En Route Flight Advisory Service, called EFOS, En Route Flight Advisory Service, and what they will give you, the information they give you is actual weather and thunderstorm information along your route of flight. And the frequency is standard over the whole country below 18,000 feet, and that standard frequency is 122.0 for Flight Watch or En Route Flight Advisory Service, primarily for actual weather and thunderstorm information along your route of flight. there is another way to get some information, weather information, when you're in the airplane and flying, and that is by listening to a transcribed weather broadcast, also known as a TWEB. A transcribed weather broadcast, or TWEB, is simply a tape recorder. It gives a tape recorded continuous message, continuous weather briefing for specific routes of flight, and it includes winds aloft and route forecast. The key thing on the transcribed weather broadcast to know is that it gives you information for a specific route of flight. Now, how can you get it while you're en route? You can listen on your navigation receiver. You can listen on either your VOR receiver or your ADF receiver. You can tune the VOR receiver to the appropriate frequency. You can tune the ADF receiver to the appropriate frequency and find out what that weather information is. What is the appropriate frequency? How do you find it out? For that, you have to take a look at the chart. Take a look on Figure 15. On Figure 15, take a look in the upper left-hand area of that chart, Area A, and we want to figure out an appropriate TWEB frequency. What you're looking for a TWEB frequency is a little black square in the lower right corner of the box, of the communications box for a navigation station. And that little box in the lower right corner, this one happens to be on the Minot Vortac, but it could be on a non-directional beacon frequency box also, tells you that they do have TWEB, the transcribed weather broadcast service. And in this particular case, for the Minot Vortac, you could listen to the TWEB on what frequency? 117.1, 117.1. And see, there's nothing to it, and you're really going to be able to get all the weather information you need like a piece of cake. Now we get to the fun and interesting stuff, doing our cross-country planning. And when you're doing your cross-country planning, one of the things that you use is a flight computer. Now, don't get buffaloed by a flight computer, because everything that you can do with a flight computer, you can also do using pencil and paper. The whole purpose of the flight computer is to make things easier for you, and if it isn't easier for you, don't worry about it. Don't use it. Just simply use pencil and paper instead. Now, the front side of the flight computer is basically a circular slide rule, and you can do the same thing with it that you can do with a circular slide rule, and that is you can multiply and you can divide. Pick up your flight computer, take a look at the front side of it, and turn it so that the 10 on the outer scale is up at the top. You want the 10 on the outer scale up at the top. Then move the inner dial so that the 10 on the inner scale is underneath the 10 on the outer scale. And that's going to have our numbers in a nice position for us to start with. Now notice that on the outside scale, we've got a label that says miles, so that the numbers on the outer scale are going to represent the miles, the distance that we travel. On the inner scale, we'll have a label that says minutes. So the inner scale is the number of minutes that we're flying. The number of minutes that we're flying, and the very far inner scale, notice that it's labeled hours. So the inner scale is minutes and the far inner scale is the hours, but the outer scale is how many miles we're flying. Now, while you've got that computer with the 10 on the outer scale next to the 10 on the inner scale, notice that there is no 1 on the computer. There is a 10, but there is no 1. So the 10 that you find on the computer could stand for 10, but it could also stand for 1, could be 10, could be 100, or could be 1,000. There is no 2 on the flight computer, so the 20 on it could stand for 2 or 20, or it could stand for 200, or it could stand for 2,000. So you have to add or subtract zeros based on the common sense, based on what you're working on, what makes common sense as far as what you're doing. Now, when you multiply and divide, what you do is you're setting a ratio in the computer. Let's assume that the FAA said to you that you've flown 1 mile in 1 minute, and they want to know how fast you're flying. You've flown 1 mile in 1 minute, and they want to know how fast you're flying. Now remember, there is no 1 on the flight computer, so what are we going to have to use to represent 1 mile instead? We're going to have to use the 10. Miles are on the outer scale, and the time is on the inner scale. We don't have a 1 for minutes either, so we'll use the 10 on the outer scale to represent 1 mile, the 10 on the inner scale to represent 1 minute. You've done 1 mile in 1 minute. Now, in your head, just in your head, if you flew 1 mile in 1 minute, how fast are you going? You're doing 60 miles an hour. But to verify that, all you have to do is look around the computer on the inner scale until you find 60 for 60 minutes. 60 minutes representing 1 hour, and it will tell you how much distance you're going to cover in 1 hour. And you're going to cover 60 miles in 60 minutes, or 60 miles per hour. What you have set up here is a 1-to-1 ratio. You've set up a 1-to-1 ratio that is valid all the way around the flight computer. Suppose that you traveled 1 mile, but instead of doing it in 1 minute, you did it in 2 minutes instead. Instead of taking you 1 minute, it took you 2 minutes. Well, you find the 10 on the outer scale, that's going to represent the 1 mile, and move the inner scale around so that the 20 on the inner scale, which represents 2 minutes, because we remember we don't have a 2, the 20 on the inner scale representing 2 minutes is next to the 10 on the outer scale representing 1 mile. So we did 1 mile in 2 minutes, or could be 10 miles in 20 minutes if you wanted to add some zeros to it. Okay, if you did 1 mile in 2 minutes instead of 1 mile in 1 minute, just in your head, how fast would you be traveling? Half as fast as you were before, so you'd be traveling 30 miles an hour. You've set up a 1-to-2 ratio. But to verify that, all you have to do is look around the inner scale of the computer, and you're looking for 60 minutes again, 60 minutes representing an hour, and when you find 60 minutes on the inner scale, the outside scale tells you how many miles you're going to have covered in an hour, which is 30 miles. So you're doing 30 miles an hour. That's the speed you are. And here again, you've got a 1-to-2 ratio, and that 1-to-2 ratio is good all the way around the flight computer. So what you have done is you're setting up ratios in the flight computer to be able to multiply or divide. Now, let's assume that the FAA said that you were flying at 100 miles an hour and you flew for 250 miles. How long would it take you to cover that distance? Well, if you fly 100 miles an hour, you're flying 100 miles every hour or every 60 minutes. So you find the 10 on the outside scale, which represents in this case 100. 10 on the outer scale for 100, and on the inner scale find 60 minutes. So you're traveling 100 miles every 60 minutes. Okay, you've got your speed set up, how fast you're going, 100 miles in 60 minutes. And you know that you're going to travel for 250 miles. So you look around the outside scale and you're looking for 25. You don't have a 250 on the flight computer, so find 25, which represents 250 miles. The next scale in will tell you how many minutes it would take, which is 150 minutes, but the far inner scale is the easiest place to read it, and that is 2 hours and 30 minutes. 150 minutes is the same as 2 hours and 30 minutes. So at 100 miles an hour, to fly for 250 miles would take you 2 hours and 30 minutes. That's how long it's going to take you. Now, suppose that you're flying, instead of at 100 miles an hour, you're flying at 120 miles an hour instead. At 120 miles an hour, you look around the outer scale until you find the 12 representing 120, because you don't have 120 on the flight computer. So you find the 12, and then you move the inner dial until the 60 is underneath the 12. You're doing 120 miles in 60 minutes, or 120 miles an hour. So you've got your ratio set up there in the flight computer. You've set in how fast you're going. How fast is 120 miles an hour? Now, let's assume that you're going to fly for 2 hours. Not a certain distance, but a certain time, 2 hours. And the question is, how far would you fly? So you look on the inner scale of the computer. 2 hours is 120 minutes. So you look on the inner scale for 12, representing 120 minutes. Now notice on the far inner scale, there's our 2 hours. We flew for 2 hours, or 120 minutes. And on the outside scale of the flight computer, you'll find how many miles you're going to have covered. And that's 240 miles that you would have covered. Now, how do you know it's 240 miles and not 24 miles? Common sense tells you that, because you're flying at a speed of 120 miles an hour, and you're going to fly for 2 hours. You're going to cover a lot more distance than 24 miles. 240 miles is the answer, because common sense tells us that. Now suppose that you're doing 140 miles an hour instead. To set up 140 miles an hour on the flight computer, you find the 14 on the outside scale, which represents the 140. Don't have 140, so we'll use the 14 instead. And we want to set up 140 miles in 60 minutes, so move the inner scale around until the 60 on the inner scale is underneath the 14, representing 140 miles. And what we've set up there is our ratio on how fast we're going. We're doing 140 miles in 60 minutes, 140 miles an hour. Okay, we know that we're going to fly for 75 miles, and we want to know how long it will take us. Now, miles. Do you find the miles on the outside scale, the inner scale, or the far inner scale? Which one? The outside scale is where you find the miles. So simply look around the outside scale until you find 75. And when you find 75, there it is. When you find 75 on the outside scale, the inner scale will tell you how many minutes it's going to take you to cover 75 miles. Okay, here's 75 miles. We've got 30, 31, 32, a hair over 32, but it looks pretty close to it. So it looks like it's going to take you about 32 minutes to cover that 75 miles. Alrighty, let's assume exactly the same speed, 140 miles an hour, but this time what we're going to do is fly for 1 hour and 30 minutes, and we want to know how many miles we'll cover. How far will we travel in 1 hour and 30 minutes? So what you do, minutes are on the inner scale. Just look around the inner scale. Don't move anything. Just look around the inner scale until you find 90 minutes. 90 minutes is 1 hour and 30 minutes. And when you find 90 minutes on the inner scale, the far inner scale says, yes, indeed, this is 1 hour and 30 minutes. And the outside scale will tell you how many miles you're going to cover in 1 hour and 30 minutes, and it's 210 miles. The 21 stands here for 210 miles. Now, how do you know for sure that it's 210 miles and not 21 miles? Common sense tells you so. And the reason is you're doing 140 miles each and every hour, and you're flying for more than an hour. You're flying for 1 hour and a half. You're going to cover a lot more distance than 21 miles. What you're going to cover is 210 miles. Let's assume that what you know is that you have flown for 23 miles and it took you 10 minutes to do it, and you'd like to figure out how fast you're flying. So what you do is you set up that ratio on the flight computer, how many miles you flew in how many minutes. And miles are on the outside scale, so you find 23 on the outside scale. And move the inner scale until 10 minutes on the inner scale is next to 23 miles on the outside scale. And you set up your ratio for how fast you're flying. 23 miles in 10 minutes. So how many miles will you cover in 60 minutes, which is an hour? Simply look around the inner scale until you find 60 minutes. And when you find 60 minutes on the inside scale, the outside scale will tell you how many miles you'll fly in 60 minutes, how many miles an hour you're doing. And it looks like 130, 35, 36, 37, 138 miles in 60 minutes, or 138 miles an hour. You figured out how fast you're flying. Now, let's assume that you're flying at exactly the same speed, 138 miles an hour. And you're going to fly for 13 minutes, and you want to know how far you're going to travel, how many miles you're going to cover. You don't have to move the inner dial because you've already got your speed set. Just simply look around the inside dial until you find the 13 for 13 minutes. And when you find 13 for 13 minutes, the outside scale will tell you how many miles you're going to cover in 13 minutes. And how many miles are you going to cover? You got it. You're going to cover 30 miles. You're going to cover 30 miles in that 13 minutes. Now, the flight computer is really very easy to use as long as you remember 4 very simple rules about it. First of all, how fast always goes first. And you set your speed in by setting in ratios. So many miles in so many minutes, so many miles an hour. That sets in your speed by setting in a ratio, and whenever you start a problem on the circular slide rule side of the computer, the first thing you always want to put on it is how fast. The second thing, the second rule for reusing the computer is that miles are always found on the outside scale of the flight computer, miles on the outer scale. The third rule is that minutes are found on the inner scale and hours are on the far inner scale, but minutes are on the inner scale. Your time is on the inside on the flight computer. And the fourth rule is, does it make sense? There's always somebody who sits down with a flight computer, works out a problem, and says, my Cherokee 140 just covered 400 miles in an hour. Well, most won't. So when you get done, when you get an answer, take a look at it and say to yourself, is this reasonable? Does it make sense according to the capability of the aircraft that I'm flying? So let's recap those rules real quick. First of all, when you're working on the circular slide rule side, what's the first thing you put on that side? How fast? How fast goes first? Miles you always find on which scale? The outer scale, inner scale, or far inner scale? Which one? Miles are on the outer scale and minutes are found on the inner scale. And the last thing you want to ask yourself, rule number 4, is, does it make sense? Is it reasonable? Does it make sense?